Welcome, I'm Matt Ahrens. I work at Delphix, and I help to create ZFS and OpenZFS, and I'm here to give you guys a little history lesson about ZFS. And hopefully you guys have a lot of questions. I'll have some stories. I'll have some questions for you guys. My first question for you, well, let me first show you. This is kind of the outline of my talk. First, I'll be talking about some kind of broad strokes. I've divided ZFS into a couple of different eras, and then be talking about following a few of these interesting features throughout their development and all the changes that have gone to them in the past 15 years. So first off, who has been using ZFS from the very beginning of FreeBSD days? So ZFS is ported to FreeBSD in 2007 by Powell. Thank you. I know you've been using it since then. Looks like a few hands, maybe 5 folks. Has anybody been using ZFS since it was a mono operating system file system, when it only ran on Solaris? A couple folks. Awesome. Old timers. So I'm going to start with the prehistory. So this is from before ZFS even existed. Why did we make ZFS? Really, it was to end the suffering. I don't know if you guys remember this era, but this was the era where hard disks were measured in the single-digit gigabytes. And if you wanted to use more than one of them, you didn't have a lot of really good options. So you could buy a really expensive storage array from a proprietary vendor that was very expensive. You usually had to pay them to have somebody sit on site and make sure that they replaced all the drives at the right time so that everything didn't break. Did anybody use one of those systems? Yeah, a couple of folks, not too many. You guys must have worked for some employers who were in the money. Second type of system that people had was array-based controllers. So this is you have a PC, you put a RAID card in there, and then you could plug a few hard drives into it, and it would do mirroring, or maybe it would do RAID 5, or at least mostly do it. These were much less expensive, but they only worked sort of, kind of, and they usually worked until one of those drives failed, and then reconstructing it was a giant pain. Anybody use one of those? Yeah, everybody used those. Yes. They should have called it a redundant array of data loss, maybe. And then the third type of systems that people use in this era was the software-based systems with a separate file system and volume manager. So coming from Sun, we had the UFS file system and the SVM for Solaris volume manager. Veritas also had a competing Veritas file system and volume manager. Did anybody use one of those? Yeah, because it was cheap, right? And maybe it came with the operating system if you're using Solaris. Veritas wasn't cheap, for sure, yeah. They had the advantages of being, in some cases, pretty inexpensive. You didn't need specialty hardware. But they were a real pain to actually set up and administer. You had all these different commands to set up disks and configure them, and then you had to administer separately the file system from the volume manager. We looked at this landscape and we said, there's got to be a better way. Computers can solve this problem. We don't need expensive proprietary arrays, and we don't need the software to be arranged in the way that it traditionally was. We looked at we took some inspiration from memory management. How many of you guys remember back in the day running dim ADM to administer your memory DIMMs? No? Nobody? Anybody remember configuring your virtual DIMMs and figuring out how to set? No? You guys don't remember that? Well, so I don't remember that either, because we never had to do that, right? With memory, when you get more memory, you take the memory, you put it into the computer, you turn the computer on, and it knows what to do with it. You don't have to think about how am I configuring my memory? How am I mapping my DIMMs to my applications? The operating system, excuse me, the operating system just handles that for you. And our vision of how storage should work was much along those lines. You should be able to put a bunch of disks into your computer, and the computer should know how to figure out where to put the data on those disks, how to get it back, and the system administrator should be expressing their intent to the storage. So if you want some data to be compressed and some data to not be compressed, you tell us that. If you, if some data needs to, if one person should have a higher quota than another person, like, hey, this guy is the guy who's paying the bills, we gotta make sure that he never gets space. Give him a really big space reservation, whereas this person tends to, just hog all the space available, give them a little quota, right? Those are the kinds of things that system administrators are thinking about. Let's let them just tell the storage system that, and we will implement it. We'll make it all work. So that was really the inspiration for ZFS before we started implementing it. Cool. Oh, and not to mention, way back in the day, this is actually before a story from before I joined Sun. The Sun kernel group, they always had this system that they used for their own home directories. And back in the 90s, somebody accidentally typoed a command to SVM, which caused it to erase all the data on the system. SVM, like a lot of these software-based volume management tools, they had their own layering, they had their own ideas of labels, and if it got confused about which devices were part of the RAID group and which weren't, then everything was all over. You might have your data there, but if the label wasn't there and it couldn't figure it out, your data was essentially all gone. So somebody typoed which disk they wanted to remove. They removed the wrong one. And then the entire department, like 1,000 engineers, are sitting there twiddling their thumbs while they went back to the tape backup. So those are the kind of experiences that we wanted to avoid with ZFS. So the early days of ZFS, I joined Sun in 2001, July of 2001, fresh out of college. It was myself and Jeff Bonwick basically sat down at a whiteboard and said, how are we going to do this? Like, what are the goals? We came up with ideas of pooled storage. That was actually an idea that Jeff had kind of predating my joining. But the idea of pooled storage, the idea that snapshots should be first-class citizens and should always be available. We shouldn't have limits on snapshots. And then we started implementing. So we actually had a proof of we'll call it a proof of concept around October of 2001, which was basically like I had implemented the DMU, which is the data management unit. We named that kind of by analogy with the MMU, the memory management unit, coming from that idea that we want to administer disks like we do DIMMs. And then Jeff implemented the SPA, which stood for the storage pool allocator. I basically implemented the DMU and a little fake SPA, and Jeff implemented the SPA and a fake DMU to consume it. And then getting towards the end of October, we kind of mashed the two together and got it barely working. And it happened that this fell on Halloween, October 31st. So we sent out an email to the whole department saying, hey, like ZFS, it lives. We have something that we can demonstrate. And so Halloween became kind of a special holiday for us. And you'll see a couple of other dates where, a couple of other years where Halloween was an important date. So during this time, we grew the team to about a dozen developers. I'll tell another story. So during this time, it was probably around 2003 or early 2004, we started actually trusting our own data to ZFS. This is obviously before we had integrated it into Solaris or anything, but just for our own team. The first machine that we created to be a file server just for the ZFS team was called Zion. So we were really big fans of the Matrix. I actually had to look this up, but the Matrix came out in 1999. So it was still prescient in our minds like 4 years later, which I guess goes to how awesome that film was. So our server was named Zion, like the home of the rebels in the Matrix. And the storage pool on it was named Tank. So So I know that people have seen the name of storage pool is named tank, because like a tank holds water and a storage pool is storage, right? But can anybody guess what, for a while we had another server that had a different storage pool. Its name wasn't tank. Anybody have a guess as to what its name was? Dozer. Yeah, its name was Dozer. So if you remember from the movie, there was Tank and Dozer were, I think, brothers who were Neo's buddies, friends in the Matrix. Cool. So getting towards the end of 2005, I'll tell that story later. So around summer of 2005, we were finishing up all those last data corruption bugs before letting anyone else use it. Excuse me. And we realized, this is going to be done like around October, so we should really integrate this on October 31st, which I think, if I remember correctly, was a Monday. So basically, the entire weekend before, Jeff is really big into the Matrix and this, the symbolism of doing this on October 31st, as we had done a few other milestones before. So we spent all weekend working. I don't know if you guys remember the early 2000s, but this is what computers looked like in the early 2000s. We did, at least we had LCDs, right? This is the prehistory days was all CRTs. You probably won't recognize me because I have some hair. But that's me at the keyboard on October 31st after spending all weekend getting all the last bugs fixed. This is part of the original team on that Monday, October 31st, 2005, actually committing the code to Solaris and making it available to, going from a couple dozen people that were using it regularly to the whole Solaris engineering organization, which was a few thousand folks, and then going out very shortly thereafter to, as part of OpenSolaris, to the broader world. How am I doing on time? Let's see. Oh, okay, let's keep going. And I'll take a break for questions in a couple slides. So the next era of ZFS was 2006, 2010. I call this like the maturation era, right? Initial development, like we got the airplane assembled. Now we got to make sure that it can actually fly. And this is the era of OpenSolaris and ZFS being used by bigger and bigger communities, and also the era of it being ported to FreeBSD and becoming available there. So a lot of this was pretty boring, like bug fixing, stuff that doesn't make for good stories. The one thing that I will mention here is that I feel like ZFS, ZFS is like, it combines the functionality of file systems and volume managers. This is something that, it's very basic. We teach this like, it's one of the first things that people learn about ZFS. But I think that really belies the complexity of what we did. Like, we really, we approached developing ZFS as a lot of us, myself especially, not being hardcore kernel system software engineers. We wanted to use higher level concepts and more layers of abstraction to be able to implement a richer feature set in ZFS. And that also means more complex behavior and more complex algorithms. So I think that without some of this enabling technology like dtrace, we really wouldn't have been able to see what was going on in the kernel to know that our algorithms were correct and performing well. I'll give a, when do I want to give an example of that? I'll give a couple examples of that in a few slides because they kind of fit into what we're doing later on. But I do really want to give credit to dtrace in terms of being able to give us these tools to see what's happening in a really dynamic system inside ZFS. Another big feature that was added here was deduplication. So dedup was actually one of the last major features developed at Sun. I think it came out in very late 2000. 2008 or early 2009. Actually, that's wrong. I think it was late 2009, early 2010. It did not get to experience the full time period of maturation. So it was a little rough around the edges when it first came out. I'll tell some, So I'll tell one story about dedupe. So, we did, actually I'll hold on to that till later. I have some more slides on dedupe later. So now we enter the modern era of ZFS being used in production. So ZFS, is now available on Illumos, FreeBSD, ZFS on Linux. This is, we started the OpenZFS project in 2002, I believe. This is the era of collaboration among contributors to ZFS from lots of different companies. With Sun/Oracle, no longer participating in any kind of open source activity. So this is also the era of OpenZFS. So we've had 4 annual OpenZFS developer summits, and this has enabled a bunch of different companies to create products based on ZFS, sell them to customers, and really base their companies or big parts of their product on ZFS. So, yeah. Again, a lot of work of making ZFS production ready and using it in production is seeing what the heck is going on and then fixing it. And dtrace really helped us a lot there. So let me tell you about one story. So the write throttle is a project that we did at Delphix a couple of years ago. And the goal here was to give more consistent write performance when the underlying storage can't keep up with the application. So the application is trying to write tons and tons of data, and the storage can't keep up. So the application has to encounter some kind of delay because we can't just keep buffering it in memory forever. So this is kind of it shows the results. So what we see here is a histogram of write latencies. So along the x-axis, this is the latencies, and then along the y-axis is like the number of writes. So we're running this workload for like a period of time, and we're looking at every write that happens. How long does it take? And then we put it into that bucket, and then that like raises this line a little bit. So before we did this work, we had this huge like spike at the end where we had tons of writes that had huge, more than 4-second latencies. So you get this really like bimodal distribution where some of your writes are super duper fast and some of them are really, really, really slow. So the project aimed to basically smooth out that performance, which you see in the orange here, where almost all of the writes are around this same 1 millisecond time, with a few stragglers that are, even those are much less than the old performance. So dtrace, it allowed us to measure this, right, which is pretty basic, right? All that you need to measure is every write system call, how long does it take, put it into a bucket, and generate this histogram. But the dynamic behavior of the system is really complicated, like how we actually achieve that. So I'll show you 2 examples of the kinds of output that we were able to get. So this is showing 1 line of output per transaction group, and it's showing us like how much data, excuse me, how much data was written, how long it took to write that data. And this next metric of percent pass 1 is kind of a measure of efficiency. So some of these are actually pretty not that efficient because basically the first pass is where we write out all of the user data, and then subsequent passes are dealing with internal ZFS metadata. The performance, the write rate. And then these columns are really telling us about the internal state of the write throttle that dictates how much those writes are going to be delayed. So the write throttle is based on the amount of dirty data. So this is showing us the most dirty data that we had during this transaction group. And then the percent of the maximum amount of dirty data. And then here it tells us the most that we throttled any operation was 73 microseconds. And then the most delay that any operation encountered was 1,000-ish microseconds. So the difference between these two numbers is that this is like, we're adding this much delay to every operation. If there's a whole bunch of operations going on at a time, then the next one has to basically get in line after all the previous ones. So if the previous one isn't scheduled to be let in for another 200 microseconds, then the next operation will have to wait the 200 mics plus 73, so 273 mics. And then this also takes that into account, and also takes into account like scheduler delay. So we might say, yeah, I want this write to be serviced in 500 microseconds, but the thread scheduler doesn't actually wake up that thread and get it to start running for 700 microseconds. So this tells us kind of what we actually achieved. So this is really valuable, but it's very coarse-grained. So this is great for monitoring the system, like after you've implemented it all, and you're like, oh, why are my writes being slow? Oh, I can look at this and see it's because I have too much dirty data. The backend can't keep up. I'm delaying it by this amount. And then it lets you kind of in one picture see, oh, well, I'm writing at this rate. Does that make sense with what my underlying storage is? And then kind of direct you to where you might want to diagnose further. But if you need to drill down even more, I wrote this other dtrace script. It shows one line of output per 100 milliseconds. So 10 times a second, we're getting a line of output here that's telling us what exactly is happening with this write throttle. So the way that the write throttle works, there's a lot, like I said, it's complicated. There's a lot of internal state here. One of the things, so we see some of the stuff that we saw before, like the percent dirty is like how much, there's a limit of how much dirty data there can be. This is how much there actually is compared to that overall limit. And then there's this new concept of undirtied. So part of the idea of the write throttle is that when somebody tells us, hey, I want to write this data, we account for that and we say, okay, great. Somebody has told us they're going to be writing 1 megabyte of data. We add that to the amount of dirty data. It increases this percent. And then when we write data out as part of syncing, we decrease that amount of dirty data. So the amount undirtied is the amount that we decrease the dirty data during that 100 milliseconds. And you can see that like at the beginning of the sync, we're undirtying a lot every 100 milliseconds, right? We're 39 megabytes in a tenth of a second. But then towards the end of the transaction group, you see we're undirtying much less. Why is that? Well, one of the reasons is that we're writing a lot less data towards the end of the transaction group. Why is that happening? Well, one of the reasons for that is shown by this last column here. So this lets us see how many writes in the system are queued, active, and the maximum that are allowed to be active. So during most of the time, we have a huge number of writes queued. And you see at the beginning there, we have basically the number active is the same as the maximum. So we're allowed to have 80. We sent 80 to the disk. So that the maximum is like how many IOs can I send to the disk? How many of these writes can I send to the disk at once? And then towards the end here, you see, oh, well, we're allowing 80, but we only actually sent 8. And this is kind of interesting. Like, I allowed 80, I sent 8. I allowed 80, I sent 8. I allowed 60, and I sent 6. Like, that's kind of interesting. That's the same digit there that repeated every time. I wonder why that is. Well, it turns out, so there's another script which shows this even more clearly, which I don't have the output here, but the reason for this is that towards the end, basically the way that the syncing works, first we allocate all the space on all the disks. So ZFS, it spreads its writes out across all the disks, and so we spread the allocations out across all the disks so that the writes will be spread out across all the disks, and then we enqueue all of those writes. So we have like a huge, there's like 10,000 writes queued there at the beginning in the AW column there. AW equals 10,000. That's the first number is the number queued. So we have these 10,000 writes queued. Great. Like there's some writes being sent to every drive, but then towards the end, what's happened is that there's one drive that's slower than some of the others. It's not able to process these writes as quickly as the other ones. So 9 out of, I think the issue here is that I have 10 drives. 9 out of the 10 have completed all of the writes that we sent it. The last one actually has 800 of those writes are just to that one drive. And the maximum is maximum for the whole pool, which is 60. And I sent 6 to that one drive. 60 because I'm allowing 6 to each of my 10 drives, which is why these numbers kind of turn out so nice and easy for us to see as humans, because it's multiple of 10. So this allowed me to see that this problem is totally unrelated to write throttle. Like this has nothing to do with the write throttle, but just dtrace allowed me, like it's everywhere that you look, you find problems, and dtrace allows you to look in all these different places. So that's really cool. One other thing I'll mention. The reason that I actually wrote this script to begin with was not to find that problem. That was just an accident. But part of the write throttle, it actually changes the number of writes that we send to the disk concurrently, depending on the amount of dirty data. So the idea here is like, if you have a lightly loaded system, then you won't have a lot of dirty data. And in that case, like, why do we need to overwhelm the disk with lots and lots of async writes? Instead, we can leave the disk idle a little bit of the time to service like synchronous reads that might come in. So that's why you see the last column there, the maximum async writes decreasing from 80 to 60 to 40. It's because the amount of dirty data is also decreasing from 62 to 37 to 35%. So that's what I was really trying to observe with this script, and ran into a bunch of other cool stuff too. All right, cool. All right, good, we're doing good on time. So now let me tell you some stories about kind of following one feature of ZFS through its whole lifetime. So send and receive was actually one of the last features to be implemented in the kind of initial phase of ZFS before we integrated it into OpenSolaris. The motivation for this is kind of interesting. So in the beginning of, beginning of 2005, Sun had opened up a new development office in Beijing, China. And they invited like any engineers who wanted to go to that office, work with the engineers there, and to kind of spread the engineering culture from from the mothership of California to this new office. So I volunteered. I thought it'd be really cool to travel, live there for a few months. So I lived there for about 4 months. And at the time, this is, I don't know if you guys remember this, but this actually predates Git. It predates Mercurial. I don't think it predates Subversion, maybe a little bit, but Sun was using it even more ancient source code management system called Teamware. The way that Teamware, has anybody used Teamware? I heard a couple, yeah, couple folks, I'm sorry. So the way Teamware worked was when you wanted to do the equivalent of like a git pull to get all the changes that happened on the trunk. It worked over NFS, so you had to have the NFS mount, And it would go into the NFS mount and traverse all of the files and check all the files' modification times to see if any files have been modified. And if they had, then it copied them over to your, over NFS to your workspace. So, this is, we're at Sun. There's like I said, thousands of engineers working on this. So there's a lot of changes being generated every day. Does anybody want to take a guess as to like how long? So I think Solaris at that time had something close to like, let's say 5 to 10 million lines of code, probably like 10,000 files or something. Anybody want to take a guess as to how long it took to do the equivalent of like a git pull from Beijing from Menlo Park to Beijing? Let's do this. I'm going to tell you the number, and then you guys tell me over under. 1 hour. Who says over? Who says under? Oh, you guys are all right. It was way more than an hour. It was like 3 hours. Obviously, that's not how long it took when you were like in the same building as the other server and the latency was measured in microseconds. But when you are on a link whose latency is measured in like hundreds of milliseconds, it is really, really slow. So I get really frustrated with this. And I was like, man, why can't we, why is it so hard to find what files were modified and send them to me? Like, that's all that I care about. So that's what kind of gave me the inspiration to create ZFS send and receive. Like one of the main design principles of ZFS send and receive is that it doesn't care about your network latency because the sending side already knows what the receiving side has. So it's like I already know that you have this previous snapshot. So all that I need to do is find the changes between that snapshot and the next one, and then blast them over the wire to you. So that's kind of why I did this to begin with. Tell you another couple of fun stories about send and receive. So, the initial send and receive, super clean design. It worked the way that we had implemented ZFS, like with the layering. This worked really well as a consumer of the DMU. So it just looks at the contents of a file system. It doesn't need to know about all the POSIX stuff. If we add different ideas of like owners and groups and support for SMB stuff, like send and receive doesn't have to care about that at all. But has anybody used ZFS send -R, the like recursive replication mode? A couple of folks. Has anybody had problems with this? Oh, you guys are doing pretty well. So the way that this works is not at all like how ZFS send works. Basically, it uses ZFS send as the underlying mechanism, but the problem is we're trying to make the receiving side look like the sending side. And within an individual file system, we have a really good mechanism for doing this, for finding the changes and sending them because we have this nice interface in the DMU. But ZFS send -R, it wants to make like all of the metadata, the ZFS level metadata, like what file systems exist, what snapshots exist, what are their names, which file system is a parent of which other file system. It's trying to make all that stuff look the same. So there's no like inherent concept of being able to like bundle up that information and plop it down on the receiving side. So it's much more kind of ad hoc where it's like the sending system says, hey, I have these file systems and snapshots in this arrangement. Here you go. And then the receiving system needs to figure out, oh, how does my configuration differ from that? And then how do I change my configuration to look like what the other guy told me his looks like? So you might have something where like I have two snapshots and I renamed both of them. And I happen to rename this one to have the same name as, like I renamed A to B and I renamed B to A. So on the receiving system, like I cannot actually reconcile this in two operations because like I can't rename A to B because B already exists, and I can't rename B to A because A already exists. Instead, I have to rename A to some temporary name, and then I have to rename B to A, and then rename the temporary name to B. So this is all like incredibly complicated and error prone. So if anybody, it does like primarily work, but It is a bit of a sore point for me because one of the design principles of ZFS is that we want all of the features to work smoothly and work well with all of the other features. And ZFS N-R, like if you use it if you don't do anything weird, it works just fine. And even if you do some weird stuff, it figures it all out. But there's a few weird things that it just can't cope with. Hopefully you've never run into them. Oh, we're running a little short on time. Okay. So let me skip receive prefetching. So I guess I'll just mention as the last point that this, ZFS has been under continual development for 15 years. Even such a fundamental feature like ZFS send and receive, like we're still making huge advances in it, even like as recently as last year with adding resumable send and receive, which I think became part of FreeBSD 11. So even people on pretty recent FreeBSD haven't had access to this. I think that just kind of goes to, I guess I'll say this is one of the things that I like about ZFS is that the fundamental design was relatively well designed, and the layering makes sense for the most part. So adding new features, adding new functionality like this, like resumable send and receive or prefetching, it fits in, and these are things that we were able to make work with everything else. So that's something that I think went pretty well. All right. So next feature that I wanted to talk about, excuse me, is scrub and resilver. So initially, back in the day, when you could do scrub and resilver from the very beginning, you could create snapshots from the very beginning. But if you took a snapshot while we were in the middle of a resilver or scrub, then the scrub would restart from the very beginning. So can anybody have any, that works fine, right? Like nobody sees any problems with this. I mean, if your resilver takes like a day and you're taking snapshots every hour, then your resilver will definitely not complete ever. So I completely rewrote the entire send and receive code in 2008. I wrote a blog entry about it if you want to read about some of the nitty-gritty details. I solved that problem. One of the interesting things about this blog entry, I went and reread it a couple days ago. One of the first public mentions of BP rewrite to use for device removal. We actually did finally implement device removal almost, 8 years later. We did implement that. It's coming soon. I will be posting a pull request hopefully next week, fingers crossed. Totally doesn't work like anything what I described in the blog post, but we have not forgotten about that feature. And again, I think one of the interesting things here is that there's still tons of work going on in this area. So, like I said, in 2008, we totally fixed that problem. But then in 2015, somebody said, hey, I noticed that it seems like sometimes when I resilver stuff, it gets to 99% done and then just sits there at 99% done, seemingly forever or for a really long time. I looked at the code and I realized, oh, actually, if you take a snapshot while you're doing the resilver, it might have to scrub that snapshot again. So it's not exactly the original problem, but it's like if you're in this situation, you can end up with the scrub kind of taking forever. So I felt really bad about that, but we did finally fix it at least. And then one of the great talks that in September, we had the most recent OpenZFS Developer Summit. There's a great talk by Sasha from Nexenta about the idea of a mostly in order resilver. So one of the reasons that scrub and resilver are so slow is that, well, for one, we have to read all the data on the pool to verify it, but we're reading that data typically in a semi-random order, which means that the disk heads end up seeking all over creation. and you end up doing it essentially at the like random IOPS rate of the drive rather than at the streaming throughput of the drive. So he's come up with a great way to do this without actually, with using only a limited amount of memory, getting almost a 10x improvement on the performance of scrubbing resilver. So I'm very hopeful that this will come soon to OpenZFS. Okay, I think we're running a little short on time. Cool. So deduplication was one of the last major features that was implemented at Sun. Has anybody had problems with the performance of dedupe? Has anybody here used dedupe? Oh, about more or less the same number. So I'm sorry, but you should have seen it back then. It was even worse. So one of the crazy things about this was that when you so if you aren't using dedupe, then when you free a block, it's like all that we're doing is like appending that block to some list of free blocks, essentially. So there's really no I/O involved immediately. It's like queuing up a little bit of work to do later, but it aggregates really nicely because we're just appending, right? So if you have like 1,000 frees, they all just go appended to the same file, and they go to one block and one write. Everything's nice and cheap. With deduplication, whenever you free a deduped block, we have to decrement the reference count of it. So now when you free a block, we might actually have to do a read to read that block from disk, to read the block of the dedupe table from disk in order to know what the reference count is, to decrement it, and then we also have to write that block of the dedupe table back to disk. So back in the bad old days, frees were actually single threaded. So if you wanted to free, let's say you had a pool with like 100 disks and you wanted to delete some file system, you do ZFS destroy, it goes and finds all the blocks that needs to be freed. Each block that we want to free, we go do the I/O to disk to read the dedupe table, and we wait for that, and then we do the next I/O to disk, wait for that, we do the next I/O, wait for that. So you have like 100 disks, 99 of them are idle, and you're just doing one random I/O at a time to try and figure out what to free, or figure out how to decrement the reference counts of the things that you're trying to free. So, we kind of fixed that problem. We made it so that at least we can issue multiple I/Os at a time to do your frees, and we did a bunch of work to like prefetch that. But this is an area that's really still very ripe for future work in terms of improving the performance of deduplication. I'm almost out of time. So let me talk a little bit about the future. So what I see as the future of ZFS is really, of OpenZFS is really twofold. One is performance. So a lot of the stuff that we talked about is performance improvement. I think the feature set of ZFS is pretty rich. It's pretty useful to a lot of people. But hardware is always getting faster. And I think we still need to concentrate on like performance of ZFS on all SSD pools. So you're using all really fast devices. Back in the day when we designed ZFS, we were thinking like CPUs are so much faster than hard disks. It's okay to spend a little bit more time like going through a bunch of layers, doing a bunch of checksums, doing compression, all this stuff. But SSDs have really kind of caught up that ratio of storage performance to CPU performance. So I think we need to do some work on streamlining the code paths in ZFS to be able to take advantage of the performance offered by all SSD pools. Performance of dedupe I mentioned, and then also performance with faster new types of storage that are kind of on the horizon, like 3D crosspoint and other things like that. I think we still need to look at how to take advantage of those best in ZFS. Like, sure, you can drop it in and it's going to perform way better, but I think that because of the layering of the software, we're leaving some performance on the table there. And then the second thing I think we should be looking at in the next 5 years is integration. So integration of ZFS with things like cloud management, with cloud ecosystems, object storage management, and then also things like integration with operating systems, like fault management on Linux and FreeBSD. I know there's a lot of work going on in those areas. So I look forward to seeing those. I know I'm exactly at the time of my talk, but I promised you guys some Q&A time. So I'm happy to stay for as long as folks want for Q&A, and I apologize for eating into your hallway track for whoever would like to stay. So questions about ZFS or the history or what kind of stuff you'd like to hear more about? Yeah.
So I know on the Linux side there's a lot of hype about containers, and of course on BSD and Solaris, I guess some of us now, have jails for a long time. Is ZFS send a good way to say send applications from one instance to another?
Yeah. Should I repeat the question? Or? Okay. Yeah. So the question was about like using ZFS send and receive to move or distribute containerized software. So I think that it is a good mechanism for moving between. It's a good mechanism if you're running ZFS send, pipe network, pipe ZFS receive. So if you're doing you're writing some kind of cloud management framework and you want to be able to move some a container instance from one machine to another, I think using send and receive is a great way to do that. Some folks have also asked about using the send stream format as a software distribution mechanism. I want to compose a web server and an application that runs on top of it, and this, that, and the other. And I'm going to take ZFS send streams that are file systems of each of them, and then post those send streams on my website or whatever, and then have people download and untar them, not untar, but receive those send streams. I think that use case is less compelling, in part because the send stream format is very specific to ZFS, and it wasn't really designed with security in mind. So it isn't really possible. It isn't easily possible to do things like, here's a send stream. I want to list all the files that are in there and extract this file. Because it works at the DMU layer rather than at the ZPL layer, it doesn't inherently know about those POSIX layer attributes like directories and owners and that kind of stuff. Instead, it relies on the ZPL, which is part of ZFS, to just interpret the bits that are in the send stream. Hopefully that kind of sort of answers your question.
Yeah.
Any other questions? Yes.
Has anyone ever tried to implement parts of low wound up in the DMU and hardware? Do hardware offload of the important operation?
So hardware offload of the DMU?
Yep.
No. I think the DMU is really high level to do hardware offload on. I mean, I guess maybe I could imagine doing hardware offload as I have a computer that's running ZFS and the DMU, and I'm going to just have a network protocol that lets me call DMU operations. I think if you look 2 or 3 layers down the stack to compression, encryption, and checksumming, those things definitely people are doing hardware offload. And there's actually been a bunch of work on ZFS on Linux to take advantage of all the AVX type of instructions for checksumming and RAID Z calculations as well. One kind of layer up from that, I think that there's a good opportunity for doing something like a SPA offload, where you separate out the allocation and storage of the data from allocation plus compression plus writing and all that stuff from the DMU and higher. So drawing that line between the DMU and the SPA, I think that can make a really interesting and compelling network protocol. Yeah, so the question was about like any work on double buffering and mmap and send file. Yeah, so for those who don't know, like I guess what you're alluding to is the fact that ZFS is not integrated with the like page cache. So if you're using mmap, then you might have like 2 copies of the data, one that was like in the page cache for mmap and one that's in ZFS's arc cache. No real direct work on that. We have been working on something called ABD for arc buff data. And the idea of that project is to essentially there's a different, somewhat related problem to this in that, so ZFS caches stuff in the arc. ZFS has a bunch of different block sizes, right? So you can have data of different block sizes. You might have like databases that are in 8K block size stuff, bulk data that's in 1 meg block size stuff, files in your home directory that are in 128K size, 128K blocks. And ZFS uses the KMM caches to allocate like, it has different KMM caches for each size of block that it could need to cache. So if your workload changes from needing to cache mostly 8K to mostly 1 meg data, then we need to like do a whole bunch of work to like tear down the 8K caches and rearrange the TLB, rearrange the memory mappings in the kernel to get these big 1 meg chunks. So the ABD project addresses that problem, which allows you to say like, I just want to back all of the data that ZFS is caching with 4K pages. Everything is just 4K pages, and if you need 1 meg, then we're going to just get a bunch of 4K pages and we'll stitch them together inside ZFS rather than doing it in the memory allocator. So that at least raises the optional possibility of some kind of integration with the page cache. Although there's still a bunch of gotchas, but it's kind of hopefully the first step towards possibly doing that. Other questions? Yes, Michael.
I believe it was Lawrence Livermore last that was doing Luster and then directly to the DMU levels.
Mm-hmm.
Are there, give a list of successful or at least ideas for DMU native applications?
So Luster, the question was about, I guess, writing other DMU consumers. Yeah, cut out the POSIX layer. So Luster, I think, has done this pretty successfully. I don't know of anyone else who's working on things like that. I haven't done a lot of research into it, so I can't really give you a great answer for other ideas right now. I could imagine things like databases, applications that are very complicated would be better suited for taking advantage of this. On the other hand, those applications are very complicated. So doing it is also very complicated. So it would definitely be like on the same order of work that, same order of magnitude work that the Luster project did its conversion, which I think was like many engineer years. Other questions? Okay, cool. Enjoy your break. Thanks, everyone.